Sorry, I'm slow at this. I just need a minute to get it presented. Okay, so you guys can see my screen, correct?
Yep. Yeah.
All right, so I took a picture from the homework and I just pasted onto what we call a Jamboard. So this figure is a little bit hard to see. I'm gonna make it a little bit bigger. Okay, so in the figure we have a constant force. So because we have a constant force, we don't need to use calculus, so that's nice. The external force is, they call it P, it's equal to 160 newtons. And it's applied to a 20 kilogram box, which is on a rough horizontal surface, which means that there's friction. While the force pushes the box a distance of 8 meters, the speed changes from 0.5 meters per second to 2.60 meters per second. So they're asking us to find the work done by friction during this process, okay? It says this is closest to. So that means that none of these will be exactly the answer. We have to figure out which one is closest. So we're looking for work due to friction. We know that net work is equal to the change in mechanical energy technically, we know E mechanical is equal to what? What makes up mechanical energy?
Potential energy plus kinetic energy.
Right, so potential plus kinetic. It could be spring potential, it could be gravitational potential, or just kinetic. In this problem, do we have gravitational potential energy?
No.
No? Okay. Do you have elastic potential energy? Are there any springs?
No.
No. So that means that our change in mechanical energy will be equal to the change in kinetic energy. So the net work will be equal to change in kinetic energy. We want to find the work done by friction, but we also have this constant force here that causes a displacement. So our net work will be comprised of what? What two forces do work on the system?
The applied force.
Okay.
And the friction.
Good. So both the applied force, the applied force is called P, so I'm going to put W sub P for the applied force. So work due to the applied force plus the work due to friction will equal the change in kinetic energy, which is 1/2 mv squared minus 1/2 mv squared. And I'm just going to consolidate that to the final minus the initial velocity. Squared. So specifically, we want to isolate just the work due to friction. So I'm going to subtract this to the other side and then plug in. So I know the work due to friction is going to be equal to 1/2 times the mass, which is 20 kilograms, times the change in velocity. The final velocity is 2.6 meters per second based on the order that it's listed. Don't forget to square it. There we go. The initial velocity is 0.5 meters per second. Again, don't forget to square it. Oh, running out of room here. Okay, and then we subtracted the work due to friction to the other side. Hold on 1 second. Sorry, the work done by the constant force to the other side. We know that work is equal to the force times the displacement, okay, and they have to be in the same direction, meaning parallel to each other. So I'm going to simplify this expression first and then plug in for the identity of work due to the applied force. So I'm going to take 0.5 times 20. I'm going to multiply that by 2.6 squared minus 0.5 squared. I get 65.1. If I have kilograms meters squared per second squared, what are my units? 65.1
Joules.
joules. Good. Okay, and then we still have to subtract the work done by the applied force P. If we take a look back here at this actual force, right, it's technically down and to the right, but the angle between the x-axis and the vector is still 30 degrees. If we replace this in the third quadrant, so we're moving it from this location and pasting it on the opposite side, right? That angle is still the same. So it's still 30 degrees below the x-axis. And it moves the object a displacement of 8 meters. So we're going to take our force, which is technically called P, times the displacement, times the cosine of theta. So you have 160 newtons. Times 8 meters. Times the cosine of 30. We'll subtract that expression from 65.1 joules to find the work that's done by the force of friction. Okay, so I have 65.1 joules, we are subtracting 1,108.51. We get a negative value of 1,043.41 joules. Okay, so first question, why is the work done by friction negative?
Because it's in the opposite direction of its movement or its displacement.
Okay. The force vector and the displacement would be opposite directions. That works. Work is a scalar quantity, right? So it doesn't technically have direction. The force of friction has direction, so you're not wrong in saying that. It's technically a scalar quantity. So when work is negative, what does that negative sign correspond to? Not the direction, but
it's taking energy away from the system.
Exactly. It takes energy away from the system. So it's reducing the velocity that the force P would have created, right? It's taking energy away from the system. The work done by the applied force is adding energy to the system. And the force of friction is taking away energy from that system. But the net overall change in the work is still positive because the object's velocity increases. But the force of friction, or the work done by friction in this case, is taking energy away from the system. Oh boy. This is way harder than I expected. Okay, good. So it's taking energy away from the system. Technically, with an answer of negative 1,043.41, our answer choice would clearly here be A. Okay, so be careful, right? There is an option, one positive, one negative. The work done by friction should be negative because it takes energy away from the system. Okay. Questions so far?
Nope.
No.
No, I'm good.
Okay. How many of us have actually tried all of the homework problems? Anybody? Okay, so let me see exactly how much time we have left. I think that we have enough time. If we do have enough time, what I'd like to do is have you guys try one first, and then us talk about it together. 10:45. Okay, just kidding. We have 3 minutes. That was quick. All right. So what I want you guys to try directly after that problem, because it's gonna make a lot more sense to you, was problem Number 28, it's the last one on the homework. In 28, they're asking you again to find the work done by friction. But this time you have to consider same setup, but you have to consider the gravitational potential energy. You can't say it's 0 because in that problem it's on an incline, so it has gravitational potential energy. So it's the same setup, the same process. You're isolating the same variable, but you have to consider one more type of energy, one more type of mechanical energy.
Sounds good.
So that's it for today. You guys can exit if you don't have any questions. If you do, you can stay behind and ask.
Bye, thank you. Bye, Ms. O'Connell. Bye, thank you.
Bye, have a good day. Oh, I gotta turn this off. How do I do that?